Supporting? Or no? And doesn't be working. You can try that. On this side.
Okay, good. Okay. Morning. Let me share the screen. Your screen. Okay, so the first thing I want to announce today is that we're going to have our second exam on Wednesday, October 27th. That'll be next week on Wednesday. So I want you to be aware of that. We're going to have our review on Monday next week. So if you want to start preparing for that, I just want to let you know, I'm still deciding on the format of the exam. There's a likelihood that the exam will be online, or at least part of it will be online. The reason for that is you'll be coding for some of the questions. So I want you to be aware of that. So I'm not 100%, and we'll make that announcement on Monday. Maybe we'll be half in class and half out of the classroom. So you have more time to code. So the reason I'm making this announcement is that if you haven't practiced, or if you're not feeling comfortable coding your solutions in Ample or in Excel, should be paying attention to that. Go back to the lectures, go back to the videos, and let me know if you have questions. I posted a solution for the labs already. I wanted to show you the solution for the lab 6, at least the solution for Ample. And I want to highlight just one thing. So basically what I observed, which is correct, I'm not saying it's wrong. Most of you just went directly and implemented the model with all parameters and all numbers into the .mod file, and you got the right solution. That's fine. But I want you to be aware of what I'm trying to explain in class about separating the data from the model. And I want to highlight the importance of that in terms of the practicality of having your model separate from the data file. For example, here I have my model, my .mod file, and as you can see, there's no numbers in here. There's just formulas. I have listed the name of a set J, which is basically telling me I'm gonna have it set representing all my products. And I'm not telling the model how many products I'm gonna have. I'm just telling the model I'm gonna have a set of products. This could be 1, this could be 10, this could be 100. It doesn't matter for this file because here I'm just stating the model. And then I'm listing the parameters or defining the parameters for each one of the parameters of this problem. So we have the profit, we have the inventory cost, we have the cutting time, the insulating time per product. So that's why you have that parameter in terms of J in J, because for each product, we're gonna have a different parameter. And then we have the parameter for the capacity of the station cutting, the capacity for insulating, the capacity for sewing, the capacity for packaging. We also have a demand that is depending on each product. So that's why D is part of a set, J in J. So that means that DI or D1 will be for product 1, D2 will be for product 2, D3 will be for product 3. And same thing for the decision variables. I have a decision X1 for product 1, X2 for product 2, and go on so on. So if you want to look at this, again, if you implement your model for the exam just by going into the .mod and implementing with all parameters in the MOD and not using a data file, that's still correct. But in the practical setting, if you were to do this, you would not do that because this is a model for if you were solving a problem for your company, most likely you'll be solving that problem continuously and you don't want to go and edit this file every time you have to solve that problem. So that's why we separate the model. You just have the model by itself to say, okay, if I need to solve this problem, I can call this model. And then the only thing I have to do is to change my data. So here's the data file. So you see at the top, I have a set J. In this case, we have 4 products. So I have a set that says, okay, I have 4 products, 1, 2, 3, and 4. If you want to name the products with the specific name, you can do that. Or for me, it's easier just to keep the numbers. It's easy in terms of implementation. And then I can just have a piece of paper saying that 1 is this, 1, 2 is this, 3 is this, and so on. And then the parameters are basically in this tabular form in which you are listing for each product the AI, W, G, D, P, and the cost at the end. And then we have the parameters for the capacity of each station. Good thing about this is if you have to solve the same problem and you have a different demand or you have a different cost or you have a different time or you have more products, you can just come here and say, okay, I have a 5th product. So I just need to do 5. And then I specify all the parameters for 5 here. Like for example, I can say this is 0.2, this is 0.1, 0.6, 0.02. And I'm making these numbers 400, and then price would be 15, and the cost will be, I don't know, 1. And that's all I need to do if I add a new product, right? I don't have to go into the MOD and try to fix the model at that each decision variable, fix every constraint. I just have to go here and add that product in the list and solve the problem again. And then that's it. So that's the advantage of keeping these 2 things separately. And again, for practical purposes, this will be the way to go. Any questions? Good.
How do you connect those files with the MOD for like in the app?
Yeah, so that's a good question. So you go back to, you're basically calling that file in the run file, the same way you're calling the MOD. So let me show you that. It's a very good question. And this is not, is it? You see, so here you're calling the model file, and then the line after that is data product2.dat. So that's the additional instruction that you have to call before. Yes, inside the run file. If you were just to use the console, you can just, let me see if I have that here. Yep. So you see, you call the model first and then the data, and then you call the solver and then solve. So the additional instruction is just this line right here, calling the data file.
And so we create one MOD file, which is this whole constraint.
Yeah, one MOD file with the model, the parameters, decision variables, objective function, and constraint, and then a separate file with the data, which is this one that I'm calling here. So they have the same name. The only difference is the extension. So one is .mod and the other one is .dat. And then if you fill this, to include product2.run. And if I expand some of these constraints, let's say expand capacity 1. It is a constraint for this problem. This is the first constraint for the problem.
So it has it x1 equals to 800, x2 to 750.
X1 equals 100, X2 equals 750, X3 equals 387.5, X4 equals 500, and then the slack for 3 is 212.
Can you open data again?
It's-
So what is this very parameter? C over score any?
It is the right-hand side, the capacity for the station. So you see, if I go to the .mod here, the right-hand side is that parameter. So if you were to increase that capacity, you just go change the value there. So for example, if I go here and say, okay, I'm going to make this 2000, and I solve this, see what we get.
So it's basically just stage. You can it's not that it's score A.
You know, by just changing that parameter, I got a 2000 at the right-hand side. Okay, solution is not changing because that extra capacity is making no difference. But yeah, if we increase the capacity for all stations, you will see that the solution will change. Okay, so bye, just go check this on your own. Let me know if you have questions. Again, for the exam purposes, you don't necessarily have to do the split. I'm making this distinction for your practical professional career. And when you go outside and you don't want to go and change that model file every time you have to, let's say, add a product or change the demand or change the capacity of your stations. You just want to keep your model fixed and then come into data files and switch those parameters that are affecting your, let's say, your weekly schedule. Instead of trying to figure out, okay, do I need to change this constraint? Do I need to add something to this constraint and so on? So again, this is available. You can check on this on your own. Make sure that I take this back to value. Now let's continue with our lecture for this week. We started the discussion on the artificial starting solution. Last week, we presented the M method as one of the strategies for finding an initial solution for a problem that has constraints, the type of constraints in which you have an equality from the beginning, or you have a greater or equal to constraint. So those problems will not be solved easily. I mean, meaning that if you try to implement the simplex method by hand and you try to solve this problem by hand, or if you need to code the simplex method on your own, you have to do an additional step to find a initial feasible solution for your problem. So at the beginning, when we were looking at the simplex method, the first examples that we saw in class, all of them has a less than or equal constraint, or have multiple less than or equal constraints. And for those type of problems, we were able to find an initial solution easily. Now we are trying to look at problems that are on have these type of constraints from the beginning, equalities and greater or equal to constraints. And as I mentioned already, we have to use an additional strategy to find an initial solution. So we talk about the M method. This method was using a artificial variables for those constraints that were equalities or greater or equal to. So those artificial variables were giving us some a way to find an initial solution, but we also wanted to penalize those artificial variables in the objective function in such a way that when we solve the problem, those artificial variables would be forced to be zero. So meaning that they have no impact on our solution at the end. So if the artificial variables are equal to zero, they have no purpose, meaning the initial purpose was to just guide us in finding an initial solution, but at the end, they're going to be equal to zero, meaning that they are not impacting the decisions that we are making for our problem. So the way we penalize them in the objective function is by using a large coefficient. In this case, we're calling this M, or a big M. That's where the name of the method is derived, the M method, which is basically creating a very big parameter in the objective function that is going to be penalizing the artificial variables. So what we do, when we do that, if we are maximizing, we are doing the negative M times R1, or times the number of artificial variables that you have. And what this is going to do is you are maximizing. So if you have a very large negative value here, you basically are going to force that artificial variable to be zero at the end of the solution, because you don't want that to impact your maximization objective. So if this is equal to 1, this is going to be minus 1,000. So that's going to have a big impact on your, in this case, if you're trying to maximize your profit, you don't want to subtract 1,000. So that's why you're forcing these artificial variables to be zero. In the same way, if you're minimizing, you do the opposite. You use a positive M, because you know if you're trying to minimize and you make this different than zero, then 1,000 is going to have a big impact on your minimization objective. So that's why we penalize. We want to make sure that at the end of the solution, those artificial values are equal to 0. And we went through some examples. I asked these questions in class, and we were able to find the solution for one example, which is listed here. So everything is in the video for Wednesday. So if you were unable to see this, you can go back and watch the video. But we also solved a lab in class, and I was able to look at the solutions. Most of you got it right. So the solution for the lab is already posted. So again, if you have questions, let me know. If you have questions now, you can ask them. Any questions about the method? No? Good. So what we're going to do now is we're going to look at a second strategy. And this strategy is called the two-phase method. And today we're also going to have a practice problem or a lab, which is going to be based also on the two-phase method. So the idea again is I go through the discussion and then I basically let you practice and see. I think that's the best way to find out if you have questions about the method. So the two-phase method, again, the same idea. We want to find an initial solution for a problem, for those problems that have a greater or equal to or equality constraints. But now we're going to look at the different strategy. The two-phase method eliminates the use of the constant m. So that's the difference. So we don't have to worry about finding a coefficient for the objective function, a large coefficient that is going to be penalizing the artificial value. However, this method requires two phases. That's why the name is two-phase method. So in the phase one, we attempt to find a starting basic feasible solution. Okay, so we try to find that initial solution, solving this phase one problem. And if we find a solution, then we can use phase two to solve the original problem. And the summary of the method is in this table. So let's read through that. The summary of the two-phase method, phase one, we put the problem in equation form. So that's the standard form. So we add the slacks, we subtract the excess variables, as you know how to work with that already. And then we're going to add the artificial variables to the constraints. So this is the same thing that we did for the M method. We start the same way. To secure a starting basic solution. Then next, we find a basic solution of the resulting equations that always minimize the sum of the artificial variables. Minimize the sum of the artificial variables. So let me make sure that you look at, or let me highlight that, because that's important. Essentially, what this is saying is we're going to solve a problem for the phase one, and then the solution of phase one will be given to phase two, and we're going to solve the original problem in phase two. So you will see why this is important in a minute. So I want to. Okay, so we're going to find a basic solution of the resultant equations, always minimize the sum of the artificial variable. So in phase one, we're going to solve a problem. It's a linear programming problem. And that problem in phase one will always be a minimization problem, always. And that's what this is saying. It's going to be a minimization problem that minimizes the sum of the artificial variables. So if you have two artificial variables, the objective function is going to be the minimization of R1 plus R2. If you have three artificial variables, the objective function of phase one will be the minimization of R1 plus R2 plus R3. That's what this is trying to say. So in phase one, the objective function always is going to be minimize the sum of the artificial variables, regardless of whether the LP is a maximization or minimization, regardless of whether your original problem is maximization or minimization. Doesn't matter for phase one, the objective function is always a minimization of the artificial variables. If the minimum value of the sum is positive, the LP problem has no feasible solution. Otherwise, proceed to phase two. Okay, so if the minimum value of the sum is positive, the LP problem has no feasible solution. Use the feasible solution from, so in phase two, once we complete phase two, we use the feasible solution from phase one as a starting basic feasible solution for the original problem. Okay, so let's look at this from a problem perspective. So this is the example. And we have the same problem actually, 4x1 plus x2, and we have three constraints. 3x1 plus x2 equals 3, so that's inequality. So we know we're going to need an artificial variable for this one. 4x1 plus 3x2. So this is also a greater or equal to constraint, so that means we're going to need an artificial variable. And then we have x1 plus x2 plus 2x2 less than or equal to 4. So if we put this into standard form, we're using E1 as a surplus in the second constraint and S1 as a slack in the third constraint. The equation form of the problem is given as follows. So see, now we are adding slack here and we are subtracting an excess variable here. So this is the standard form, the equation form. And as we saw on our previous lecture, we know that it will be difficult for us to, or impossible actually, to find an initial solution for this problem without the artificial variables. So in phase one, the attempt is to find a starting basic feasible solution for the original problem. So what we're going to do is we're going to replace the original objective function, z, regardless, again, one more time, I'm making that statement, regardless of minimizing or maximizing, with minimizing r. Okay, so we're gonna take the objective function of the problem. We're gonna, yes. Oh, so we haven't added the artificial variables yet at this point. Why? We should add it here, but we haven't done it yet because we're just putting the problem into standard form. We're gonna do it now. So first thing is we set up the problem into the equation form. Now we're gonna solve the problem and you will see how that looks in a minute. Okay? Yes. So we're gonna minimize the objective function for phase one is gonna be minimizing the sum of the r. R equals the sum of the artificial variables, and solving this new minimization problem, the objective function is going to be this. Okay, so this is going to be for phase one. We are not going to take the original objective function. We are not going to use the original objective function to solve phase one. We're going to take this objective function, which is basically saying we want to minimize the summation of the values of the artificial variables. So the idea again is to find an initial solution that is going to have to use the artificial variables, but at the end of solving phase one, we know that the artificial variables will have a value of 0 because we are minimizing them. We want to minimize them. We want to find an initial solution, but we want them to be as close as 0 as possible. So this is what you were referring to. So now you see phase one is no longer no longer using the original objective function. We substitute the original objective function by this minimization of the sum of the artificial variables. We have R1 and R2, R1 plus R2, because we have we need two artificial variables in this problem. We need an artificial variable for this constraint and one for this constraint. If we only needed one, we will minimize only R1. If we needed 3, the minimization will be for R1 plus R2 plus R3. If we needed 5, you will have 5 artificial variables in the objective function. So that minimization of R is going to be depending on the number of artificial variables that you have in your problem. So in this case, we have only 2. R1 for the first constraint, R2 for the second constraint. So that's why our objective function is the minimization of R1 plus R2. Again, if we only had one artificial variable, we were minimizing only that artificial variable. In this case, we have two, so we are minimizing the summation of those two. So now that we have the problem in this format, you're adding artificial variables, and we have a slack. We know that we can find a starting basic solution using the artificials and the slack variable. And that solution is basically saying x1, x2, and e1 are going to be 0, and we're going to solve for r1, r2, and s1. So the values will be 3, 6, and 4. So this is how the Tableau will look like. If we will set up this in a Tableau format, you will have x1, x2, e1, r1, r2, s1, and on the right-hand side. Again, when you set up your objective function, you're moving everything to the left before setting up the Tableau. So this is so we have r minus r1 minus r2 equals 0. So that's why this is negative and this is negative. Oh, why is the second constraint have the artificial variables? Because artificial variables are only added to constraints that are equalities and greater or equal to. We don't need them for these type of constraints because we have the slack variable that can help us find an initial solution. Okay, so we have the Tableau now, and what's the problem? Do you see any problem here? Like when you look at the identity matrix, right? For the basics, this is gonna be our identity matrix. What is the problem? We have these negative values, right? We need to make them 0. And we need to use the Gauss-Jordan method to make those equal to 0. So this is in the right format. So that's what we're gonna do next. Before proceeding with the simplex method computations, the R row must be made consistent with the rest of the Tableau. R1 and R2 are substituted out in the R row by using the following row operation. So basically what we need to do is we need to multiply this by -1 and add it to row 0. And then, I'm sorry, this should be +1. And this one by +1 plus row 0. Which is what this equation is trying to illustrate. Why we want to do that? Because this has to be equal to 0 before we can apply the simplex method. And this has to be equal to 0. How do you remember that that's needed? We can show that mathematically. If we are saying that, okay, that's what we're stating here is that R1 equals 3, R2 equals 6, and S1 equals 4. That's our initial solution after setting up this Tableau. That's showing up here too. R1 equals 3, R2 equals 6, S1 equals 4. That is not consistent with this objective function, right? Because the objective function value is here. This is the objective function value at this point. And what we are saying is R1 equals 3, R2 equals 6, and S1 equals 4. And we are saying the objective function value equals 0, but R1 plus R2 is not equal to 0. R1 plus R2 is 3 plus 6, and that should be equal to 9. So this value should be 9, which is not true if we don't make this equal to 0. That's why we need to make this equal to 0. You'll see that after making those operations, its right-hand side value will be equal to 9. And it's going to be consistent with the solution. Okay, so mathematically, we can show that. Right now, we're saying the objective function is 0, but when we look at the objective function, R1 plus R2, R1 is 3, R2 is 6, that should be equal to 9, not equal to 0. So that's why we need to make this to 0 and 0. That will make this consistent with the actual solution. So after going through those iterations, you'll see that after making the Gauss-Jordan iterations that I listed here, so we can do that here. So we are multiplying this by positive 1 and then add it to row 0. So that would be 3 times 1 plus 0. So that will be 3. This will be 1 plus 0. This will be 1, 0. This will be 0, 1. There's going to be 0. This is going to be minus 1. This is going to be 0. And this is going to be 3. Okay, so that's after making the first Gauss-Jordan operation. Now we're going to do the second one. We're going to multiply this by positive 1, and we're going to add this to row 0. So this is going to be 1 times 4 is going to be plus 3 is 7. Yes, I'm calling this 0, 1, 2, and 3. Row 0, row 1, row 2, and row 3. Yes. So 3 times 1 plus 0, I'm sorry, plus 1, this is 4. Negative 1 plus times 1, this is negative 1. This is 0. This is 0. This is 0. This is 6. So now this is 9. So this new row 0 will be 7, 4, minus 1, 0, 0, 0, and 9. After making these two operations. Okay, so now we have the tableau in the format that we needed to find that initial solution for our problem. So what we're going to do at this point is to apply the simplex method. So after how do we call this? So after setting the problem row 0, we now solve phase 1 using the simplex method. We're actually make that solution consistent, but the point was to make this coefficient 0, so this will resemble the identity matrix. But by doing that, we are making sure that this has the right format. Yes, the right solution for the problem. So now we have the table in this format. This is the right format. So after saying the problem row 0, we now solve phase 1 using the simplex method. So this is a minimization problem. And the question is, do we have the optimal solution? Why is this a minimization problem? Remember, phase 1 is always a minimization problem. Minimize R1 plus R2. So we are minimizing this. So we look at row 0 again. We call this row 0. And for minimization, we want to look if we have any positive coefficient for the decision variables. Yes, we have two positive coefficients, 7 and 4. So we choose the largest positive coefficient for minimization. So that will be 7. So that means that this guy, x1, can enter the solution. And then we're going to do the minimum ratio test to identify which one of these basic variables are going to leave. So that's what we are doing here. We are doing the minimum ratio test. So this is 3/3 equals 1. This is 6/4 equals 1.5. And this is 4/1 equals 4. So the minimum is 1. So that means that R1 is leaving, X1 is entering. So that's why X1 is taking the place for R1. So if that's the case, we now need to make this column looks like this one, right? Because that decision variable is entering the basics. So we have to make the elementary row operations arrows to transform that into this new tableau. Okay, so at this point, I'm assuming that you know what we are doing. I'm not going to go into doing all the operations. So we do the elementary row operations and what? The row operations. Okay. So what we are trying to do again is to make this consistent. So the basic variable R1 is leaving, X1 is replacing. So what we want is to make this column 0, 1, 0, 0, right? So the first operation, actually, I'm gonna ask you guys, I think that's, so what would be your first operation? What you would do first? If you need to make this equal to 0, what would you do? Yes, so you multiply this by -7 and you add these to row 0. Okay. So I'm sorry, let's see. But before you do that, how do you make this 1? How do you make this 1? These 3 equal to 1. You have to multiply all this by 1/3, right? You multiply all that by 1/3. That's how this makes 1. This becomes 1/3. This is 0. This is 1/3. This is 0, 0, and 3/3 is 1. Okay, so that's by multiplying the row by 1/3. And then using this, you multiply by -7, and that will be -7 plus 7 equals 0. -7 by 1/3 is gonna be minus, so this is 1/3. So it's -7/3 plus 4, and that should be equal to 1.7. Then we have -7 times 0 is 0 plus -1 is -1. -7 by 1/3. So this is 1/3 minus 1/3. So it's positive 1/3. So -7 thirds plus 0 equals -2.3. This is 0, this is 0, this is -7 times 1 is -7 plus 9 is +2. And that will be the row 0 computation. Be able to follow right there? So we repeat that for the other 2 rows. And those are the elementary row operations that we discussed in our review for linear algebra.
So you replace row R1, this time make the one, zero.
Yes.
There's four.
Yeah, row 0 is 0, row 2 and row 3 are 0. Because since x1 is taking R1, is replacing R1 as the basics, this is the format for the basic variables. So since you're replacing R1, you have to be represented using that format for the original variable. So that's why this becomes 0, 1, 0, 0, because you are replacing R1 in the basics. So after completing this first iteration, we look again into row 0 and we find out that we are not done. We still have a positive coefficient in row 0, which is this one. So that means that our x2 is now entering the solution. And if we perform the minimum ratio test, this is going to be 1 over 1/3 equals 3, be 2 over 1.67. So that's, what is that? 133, 5/3. So, yeah, so yes, this is 5/3. So that's 1.2, and this is 3 over 1.7. Seven-thirds equals 1.8. So the minimum is this one. So R2 is leaving, X2 is entering the solution. So now we need to make the column corresponding to X2 looks like this one. Okay, so we perform the elementary row operations. You see now that column looks like that. This looks like the column originally for R1. So at this point, we have no positive coefficients here. The objective function value is what we wanted, right? The minimization of the artificial variables equals 0. So that's what we wanted. The artificial variables are out of the objective function. And this is the solution for phase 1. And this is giving us the initial solution for our problem. X1 equals 3 over 5, X2 equals 6 over 5, S1 equals 1. So we went through all this process just to find an initial solution for our problem. Okay. So as you can see, the two-phase method is a little bit longer than the big M method. The only advantage of the two-phase method is that we don't need to find a coefficient M to solve our problem. But the disadvantage is this takes more time. So
X2
yeah, so we're not done yet. This is phase 1. We have to move to phase 2. So we haven't.
Yeah,
Yeah.
I'm trying to understand how we get in the column X2.
Zeros and 1 and 0?
Yeah.
Because we are performing the elementary row operations to R2 is leaving. So
How did we get there?
this?
Yeah.
Yes, again, I'm assuming that we already know what's going on between iterations. So you have to perform the elementary row operations to move from this point to this point. Okay, so we have to make this guy look like this guy, because X2 is replacing R2 in the basics. So in order to make this column represent this, you have to perform the elementary row operations from this tableau to this tableau.
Yeah, but you can just, for example, X1. How did we get 0?
Where?
X1,
This?
0?
This?
Yeah.
Okay, so I guess, okay, so the idea is that every time you enter and decide who's going to enter and who's going to leave, you have to make sure that each variable that you're entering is replacing the variable that is leaving. So you have to make sure that, for example, when X1, we decided that X1 is going to enter and it's replacing R1, this column now has to look like R1 because it's replacing that variable in the solution. Same thing here. We decided that X2 is going to enter, largest positive coefficient, and we decided that R2 is leaving because of the minimum ratio test. So now X2 is replacing R2. So X2, the column has to look like this one. Okay. So how do we go from this column for X1 to this column? Do you remember what we did?
Yeah.
We did the elementary row operation, right?
I mean, my point, I guess, because in that example was simple, these numbers, but having 1.7.3, I honestly don't see how you do row operations.
Oh, this one?
Yeah.
Yeah, I guess the question is about how to deal with the fractional and the decimal places, right? More like that. Okay, so in this case, I put the fractional, not the fractions, but I put the decimal places and the decimal numbers in here instead of the fractions. I think the best way to handle this will be to keep the fractional values. I think that will be easier in terms of computational. So yeah, I see your point, but the idea is, let's say that this is a fractional number. We say that this was 1.667. You remember what number is that in terms of fractional? No. Okay, so let me see. I can find out. 5/3? Yes. Yeah, so my advice is instead of putting the decimal places, I guess I was solving this with a calculator. Keep the fractional numbers and it will be easier for you to handle. So in this case, you would multiply by 3/5, 3/5, and then this will become 1, which is here. Yes.
But this is, I mean, this is, I got it. X2 row, but how about, for example, X1 row, the first row?
This one? This one?
Yeah. How did we get 0 there? I mean,
This?
no. You're talking about the X. Yeah.
This one? So now this will be, I mean, once you multiply this by 3/5, this will become 1. So it will be easier now to manage because you multiply this by minus 1/3 and then you add it to this. Okay. So once you get that 1, the rest of the operation is just multiplying by the opposite in terms of sign or the coefficients in that column. Yes, you have a question?
I just want to make sure. So you know that X1 in first matrix is because of the height, because of the size.
Largest positive coefficient for minimization. Yes.
And then R1 leaving.
Because of the minimum ratio test. Yes. If you look at the minimum here, 1.2, that's telling you that decision variable. Any other question? Okay. So we got to this table here. So at this point, we see that there's no positive coefficient. We have zeros and negatives, so we are done. This is the optimal solution for phase one. So we have a solution in terms of x1, x2, and s1. And again, since we are minimizing for the artificial variables, what we want to see here is a zero. If we end up with a positive value, then this problem has no solution. Why is that? Because having a value of 1, 2, or 3 in the optimal tableau for phase one is telling you that you cannot find an initial solution without an artificial value. If that's the case, then the problem has no solution. If you end up with an objective function equal to 0, what this is telling you is, okay, you can find an initial solution for your problem in terms of x1, x2, and s1. You have those coefficients, and that solution has a value for 0 for your artificial value. Meaning that in this case, the artificial variables are out, they're not part of the basic variable. So if they are not part of the basic variables, they are equal to 0. But you can end up with an artificial variable here in the basics, as long as that artificial variable has a value of 0 here, then it's not going to impact your solution because it's equal to 0. Okay, so what we want to see here at the end on the first iteration or phase one is a 0 for the minimization of R1 and R2. If we have a minimization of R1 and R2, we want to get a 0 here in the optimal solution. If for some reason we end up here and we have a value that is different than 0, that means that an artificial variable is greater than 0, and that means that the solution, the problem has no solution. We cannot find an initial solution without an artificial variable. That means the problem has no solution. The goal of this phase one is to find an initial solution. We just want to use the artificial variables to help us find that initial solution. But we don't want the artificial variables to be part of the solution. And that's the whole purpose of minimizing the summation of the artificial variables. We want them to be 0 at the end of this process. Want them to be 0. We don't want them to be part of the solution of the problem. If they are part of the solution of the problem means that when you set up your constraints, there's no feasible region. What that means? That's the meaning of that. Okay, so we are not done. At this point, what we want to do is to go to phase two. Okay, so the new R row is used to solve phase one of the problem, which is the following optimal tableau. So this is the same tableau that we got here at the end. Because minimum R equals 0, phase one produces the basic feasible solution x1 equals 3/5, x2 equals 6/5, and s1 equals 1. At this point, the artificial variables have completed their mission, and we can eliminate their columns altogether from the tableau and move to phase two. Okay, so what we are saying is they did what they're supposed to do. We no longer need them. So this is how your new problem is going to look like. So now we are coming back, we are bringing back the original objective function in phase two. This is the original objective function. And these constraints are based on the coefficients from this tableau. So you see, for the first constraint, we have x1 plus 1/5 E1 less than or equal to, I think, was that constraint, or equality to 3/5. On the second constraint, we have x2 minus 3/5 equals 6/5. And in the third constraint, we have E1 plus S1 equals 1. So after phase one, these are the coefficients for the constraints. We are building those constraints based on this tableau, and we are bringing back the original objective function. So now we want to, what these constraints are doing is, if you have this constraint, you find an initial solution for your problem. Basically, what this is saying is, to find an initial solution, let's use these constraints, okay? Which are based on the original problem. And let's bring back to the original objective function. So phase one has transformed the original constraints equations in a manner that provides a starting basic feasible solution. So if we set up this in the Tableau format, again, we need to move this objective function coefficients to the left. So this is z minus 4x1 minus x2. So those coefficients are now showing up in the objective function, minus 4, minus 1. And these are the coefficients for the constraints. Okay, so we face the same issue now. Bring this objective function, put that in the objective function. And then we are trying to make this identity matrix columns consistent with the initial solution for our problem. So what this is saying, based on our Tableau, so the basic variables, this is going to be x1, this is going to be x2, and this is going to be s1. So the solution for this problem is saying that x1 equals 3 over 5, x2 equals 6 over 5, and s1 equals 1. If you look at the objective function value for this table, this objective function value equals 0. But that's not consistent with this. The objective function value is 4x1 plus x2. If we substitute those current values here, you'll see that that is not equal to 0. So what this means is we have to make these two problems consistent with the identity matrix. We have to make this equal to 0. We have to make this equal to 0 in order to solve the second phase, before we attempt to solve the phase 2. So how do you make this equal to 0 and this equal to 0? You perform the elementary row operations. To make this equal to 0 and then this equal to 0. And that's what you're going to see on the next slide. Again, because the basic variables x1 and x2 have non-zero coefficients in the 0, they must be substituted out using this operation. So what this is saying, and this is x1, x2, x1. What this is saying, I'm going to multiply this by 4, and then add that to row 0. And we're going to multiply this by 1 and add that to row 0. So we can make this equal to 0, and we can make this equal to 0. So the initial Tableau, phase 2, is thus given as follows. So after performing the elementary row operations, this is the initial Tableau for phase 2. You see now that the objective function value is no longer equal to 0. This is the value for z now. This is x1, this is x2, this is 1. These are the basic. And because we are minimizing, now we can solve this problem. If you remember, the original objective function is the minimization. So since we are minimizing now, E1 must enter the solution. We find the largest positive coefficient. This will be 1 over 5. And the application of the simplex method will produce the optimum in one iteration. So for the next Tableau, we're going to enter E1. and we're gonna do the minimum ratio test. This is gonna be 3/5 divided by 1. So this is 3/5. This is gonna be 6/5 divided by this is wrong. This 3/5. Yeah, I'm sorry, I'm confused. Gonna be 3/5 divided by 1/5. And this is gonna be 15/5 equals 3. This is gonna be 6/5 divided by minus 3/5. So this undefined, negative. And this is gonna be 1/1, which is equal to 1. So that means that S1 is going to leave. So in our next iteration, we're gonna enter E1.
Row 2 is not.
This minimum ratio test?
Yeah, we can.
No. Negative, non-zeros, yes.
First column have like a 1.
Yes,
Zero, so that would be-
here. Yes. So say that again.
So we have, for this X2 is equals negative.
Yeah. So the minimum ratio test has to be positive. Yeah, so if it is negative, we don't take that into account. Is undefined. And if you're dividing by 0, is also undefined. So we don't take that into account either. 0 is undefined, negative is not taken into account. Only positive ratios. Okay. So after completing this iteration, we'll produce the optimal value. After making E1 substitute S1, we'll get the optimal solution for this problem. Okay, so you can do that on your own. What I want to, before we end the lecture, is to complete the explanation. So the removal of the artificial variables and their columns at the end of phase 1 can take place only when they are all non-basic. Okay, so we can remove the columns if the artificial variables are non-basic. If one or more artificial variables are basic at 0 level, then the removal requires the following additional steps. We select a 0 artificial variable to leave the basic solution and designate this row as the pivot row. The entering variable can be any non-basic, a non-artificial variable with a non-zero, positive or negative quotation in the pivot row, and we perform the associated simplex iteration. Remove the column of the just leaving artificial variable from the tableau. If all the 0 artificial variables have been removed, go to phase 2, otherwise go to step 1. So we will see this in the lab. I know I thought we were going to have more time today. What I'm going to do is I'm going to extend the time for the lab until Wednesday night. We're going to go over that on Wednesday in class. I will encourage you to look at that lab today, try to solve it, and then come with questions on Wednesday. I think that would be the best thing to do. If not, then we will start the discussion and we'll address those questions in class on Wednesday. But I'm going to extend the lab due date for Wednesday night. We're going to continue this discussion on Wednesday. I encourage you again to try to solve that two-phase method using the lab problem on your own, and then come with questions on Wednesday. That will facilitate your understanding of the method. Okay, so again, it's not due tonight. It's going to be due on Wednesday night. We're going to go over that lab in class on Wednesday. Any questions? Okay, so I'm going to post the video. I'm going to post the notes for today. Go back, review, and try to attempt the lab for the one that was assigned today. and then come with questions on Wednesday. Any comments? Nope. So I'll see you on Wednesday.